Yeah, well, let me thank Tom and all the other organizers for putting this a really nice conference so far. And yeah, so they asked me to lead this discussion on fault-tolerant computing, which is obviously a broad topic. So what I took this to mean is kind of two related questions, two ways of looking at the same question maybe, which is how do we design quantum simulation algorithms around fault-tolerant architectures? And how do we design fault-tolerant architectures around quantum simulation algorithms? And so to give a little bit of background, I'll walk through maybe like 15 minutes of slides, and then we can break out into the discussion rooms. And so the rough outline is I'll give a brief outline overview of fault-tolerant quantum computing. How does this really work? I'm assuming there's some chemists in the audience that maybe haven't thought about this so carefully. So maybe it's good to understand a bit the requirements or the constraints that are placed on quantum algorithms by working within like a fault-tolerant architecture. I'll do like one slide on where do we stand in achieving fault tolerance experimentally. And then there are sort of 5 questions for the breakout discussions that were suggested by the organizers, and I'll briefly give some thoughts on them just to kind of seed the discussion that can go on in the breakout groups. So why do we need quantum error correction? This is probably obvious for everyone. If we want a quantum algorithm with n gates, we need some fidelity f such that f to the n is larger than 0. This is assuming that there's no magic cancellation of errors and so on. And so, basically the physical fidelity of a qubit places some constraint on how many gates we can execute. And so that, the question is, can we do something interesting without error correction? Maybe that's the right question to ask. And that's, of course, the whole discussion of, what are the interesting things we can do with like a NISQ era quantum computer. That's the topic of many other discussion sessions. But we do know that if we can do maybe 10 to the 10, 10 to the 9, somewhere around there gates, we can do some interesting calculations, but that requires us to have a fidelity that's better than 1 minus 10 to the minus 9. So very, very close to 1. That is better than even the most optimistic outlook for any qubit platform we know of. So it seems incredibly unlikely that these types of algorithms can be run directly on the physical hardware without some error correction. And so basically, if you think about long-term quantum computing, error correction must be the goal eventually. So how does quantum error correction work? The basic idea put forward by Shaw in the mid-90s is to encode a single qubit into many physical qubits. And so just to walk through a super basic example, this is a code that was invented by Laflamme and his collaborators in 1996. And so this is a code that encodes a single logical qubit, as we call it, into 5 physical qubits. And the code is defined by these so-called stabilizer operators. These are products of Pauli operators that makes it a stabilizer code. It doesn't have to be that way, but basically all codes that are being discussed fall into that category. And you can think of the stabilizers as sort of the checks that you do on the code to double check whether an error has occurred. And so these are commuting Pauli operators, and there's 4 of them. You have 5 qubits, so your Hilbert space is 2 to the 5 dimensional. Those 4 different Pauli operators that commute with each other but don't generate each other. You can think of each measurement of one of those as cutting your Hilbert space in half. So if you have a 2 to the 5 dimensional Hilbert space, you do 4 measurements. So you divide that by 2 to the 4. You have 2 states remaining. So there are 2 states that are the simultaneous eigenstates of all of these 4 stabilizer operators. So that's how you can think of the code stabilizer, sort of cutting your large dimensional physical Hilbert space down to the 2-dimensional logical Hilbert space. So that's one thing you need to do to have such a code. The other requirement is that you can identify the errors by the measurement outcomes. And so that's kind of this table here. So this table here is if a particular Pauli error had occurred. So for example, if you had accidentally applied Pauli X on qubit 1, all of these 4 would have 3 would have measurement outcome 1, but this last one would have 0, but this last one would have measurement outcome 1. Or if, a Y error had occurred on the first qubit, then there'd be a 0 outcome on stabilizer 2, but 1, 3, and 4 would have stabilizer outcome 1, and so on. You can look at this table and you can see that all the columns are unique. And what that means is that by looking at these 4 measurement outcomes, you can uniquely identify which single qubit error, Pauli error, had occurred on the input state. And so this allows you to uniquely identify, and in this case also correct the errors. And so you can protect the encoded qubit space state against any such single qubit errors. Now that's not sort of quite the full story yet. To really make this fault tolerant, you have to think about what happens, for example, if errors occur between stabilizer measurements. There's various tricks in the literature, which I don't really want to go into. You basically repeat the measurement of certain stabilizers, and there's a whole body of literature on figuring out how to do this in the presence of errors occurring at any time, in the presence of actual measurement errors where your stabilizer readout is wrong, and all such kind of things. Another complication that's important is that, of course, in most architectures, you can't directly go and measure this product of 4 Pauli operators. So you need to introduce auxiliary qubits, entangle the data qubits with those, and so on, to actually achieve the measurements. So the real world is more complicated than this. So what does this achieve? So this sort of gets you part of the way to the solution. But the problem is you could still have 2 errors occur while, say, you're doing the stabilizer measurements, and that you cannot detect, that you cannot correct. So somehow what you've done is you've improved your maximum length of a computation from what you can do on the physical qubits to what you can do until you're unlucky enough that 2 errors occur in a single round of error correction. So this is sort of a fixed improvement. If you wanted to run a longer computation, you'd still have to make better physical qubits to make the probability of having 2 errors in one single measurement low enough. The solution to this is to construct families of codes that sort of systematically use more and more qubits to encode a single logical qubit, and thereby can correct more and more errors. And there's a couple of ideas from the 90s that achieve this. One idea is concatenation. So you sort of sandwich these codes. You use a logical qubit of one code as the physical qubit of the next code. And there are families of codes, like in Schoen's famous 96 paper, use these so-called self-dual Reed-Miller codes. But the key takeaway is that what all of these families of codes achieve is that if you make them bigger and bigger, the logical error rate gets smaller and smaller if your physical error rate is below some threshold. So basically, if your physical error rate is above some threshold, it gets worse and worse if you make the code larger and larger. And if it's below some threshold, it gets better and better. If this sounds like a phase transition, then that's because that's exactly what's going on. This can be viewed as sort of a classical type of phase transition in the ability of these codes to correct errors. Now, there's a lot of different codes that people are considering, but there's maybe one that stands out as likely the most practical code, and that's the surface code. So I put the slightly tongue-in-cheek title here that all quantum computers will be topological in the end. You can choose to use topological qubits like we do at Microsoft, or you can choose to do different ones. But in the end, most really scalable and practical correction schemes use topological somewhere in there. And so in particular, this idea due to Kitaev in the late 90s is to do fault-tolerant quantum computation by anyons, as the title of the paper says. What he found is that a topological phase can be encoded in a Hamiltonian that has a very simple structure, and that also has the structure of a stabilizer code. So you have the qubits arranged on the edges of the square lattice that's shown in the picture here. And there's 2 types of stabilizer operators. We have these star operators or vertex operators that involve the 4 qubits around the vertex of this lattice, and it's just the product of the Pauli X operators and those. And then you have the Z-type stabilizer, which is the 4 qubits around the plaquette of the lattice, and it's the Z Paulis around those. And he showed that this system, if you just find the simultaneous ground state of all of these terms in the Hamiltonian, or you just keep measuring those stabilizers. You get a single qubit if you either put the system on a torus, that's sort of where the original name toric code comes from. That would give you 2 qubits, in fact. Putting the system on a torus is not super practical, but you can also achieve this by having different choices of boundary conditions. So for example, you can just have a square patch of the surface code and have sort of a smooth boundary at the top and a rough boundary at the side, and that'll also encode a single logical qubit. And again, the sort of error rate of the logical qubit gets exponentially better as you make this patch of the surface code larger and larger. So what's the threshold of this surface code? It's maybe important to note that the threshold is somehow not a single unique number, but to really have a useful threshold, one needs to take the implementation details into account. So as I mentioned before, there's no physical qubit platform that can actually measure these stabilizers, which are these, products of 4 Pauli operators around a vertex or plaquette, directly. I think all the plausible architectures have to construct this measurement by adding these auxiliary qubits, which are the black circles shown in this picture here, then doing some entangling operation between the auxiliary qubit and its 4 neighboring data qubits. So basically, there's a series of C knots, and then some final measurement on the auxiliary qubit. And of course, in your error, to really estimate the threshold, you need to include possible errors on each of those steps. And so, the threshold will then depend on these implementation details, what type of entangling operations do you use, and all of that. And this picture on the right here, this is from a paper by Austin Fowler and collaborators in 2012. That's the picture I showed previously. That's exactly if you apply, if you randomly apply a Pauli operator after each step, after each Clifford gate in the circuit, and then you end up with some threshold for that specific implementation of this specific code. But the caveat is that it's pretty specific to this implementation, and also that there's many other error models that are possible. So there could be, for example, biased Pauli errors, where one type of Pauli error is much more likely than other types of Pauli errors, and that can significantly change the threshold. And that was, for example, exploited in a recent Amazon paper, because they have a qubit platform where one type of Pauli is much more likely than a different type of Pauli. You could have errors that are not of this Pauli type at all, and so on and so forth. The next question is, now we have these logical qubits, how do we actually do operations on them? On these topological codes, this can be constructed from understanding topological quantum field theory. And so basically, the way you do operations is by braiding of anyons. I don't want to really go into the details here, but I think for the surface codes, there's sort of 3 broader ways of doing this. One is to basically apply what's called a Wilson operator in the TQFT side, which you can think of as moving an abelian anyon through your system. This turns out in these systems here to be a transversal gate. Transversal means that you're applying some logical gate by just applying a gate to some subset of all the physical qubits, but all in a single time step. So you can do one logical gate operation in a single, basically, time step by just simultaneously applying some single qubit gate to some, in this case, string of physical qubits. That's one way to do it. Another way to do it is to recognize that while anyons in this theory are abelian, so they don't give you interesting braiding, the defects are not abelian, and so you can introduce defects into this topological theory, and you can braid those defects around each other. The way that looks like in the surface code implementation is that you just sort of choose to not measure the stabilizer on some patch of your system, and then you make several of these patches and you move them around each other. And that actually turns out to do logical gate operations. And the final way to do it is to emulate the braiding by measurement. This is an approach that's called lattice surgery. And here what you do is you basically take these patches of surface code as shown on the right picture here. Each patch encodes a logical qubit. And then you can do measurements between adjacent qubits by doing particular measurements along sort of the lines that glue these patches together. And for various reasons that I don't want to get into, that is, I think, by many people believed to be the most efficient practical implementation of logical operations on these surface codes. And so that requires turning all of your gate operations into measurement operations, which can be done. Why do we need to think about this? One reason we need to think about this is because we need to think about the costs of implementing various gates that we want to use in the quantum algorithms on these fault-tolerant architectures. And one of the key distinction here is between Clifford gates and non-Clifford gates. So all of these approaches that are discussed on the previous slide have one thing in common, which is that they only generate Clifford gates. So the Clifford gates, that's the class of gates that transform Pauli's back to Pauli's under conjugation. So Clifford gate is a gate such that if you take a Pauli gate P and you conjugate it by the Clifford gate C, you get a new Pauli gate. And the problem with these is that they're not universal for quantum computation. Indeed, a computation that's composed purely of these Clifford gates can be classically simulated. And so to do something that can't be classically simulated, you need to augment these with at least one non-Clifford gate. And there's different, you could choose any gate really. There's a couple of common choices. The most common one is the so-called T gate. And the T gate is basically the fourth root of the S gate. So it's a phase gate with a rotation angle of pi over 8, basically. You could make other choices. You could, for example, use a Toffoli gate just as well. And another way is to provide states. So the so-called T state here, which is just if you take, say, the plus state, the eigenstate of the X operator, and you apply the T gate to it, you get this T state. That sort of serves the same purpose because if you have this state, you can apply the T gate to another qubit with just a 2-qubit measurement. Why do we choose this particular T gate and not some other rotation? Reason is that there's a procedure called magic state distillation. And what it does at a very high level is that it takes some large number of bad T states, so sort of inaccurate realizations of this T state, and turns it into a few good T states. So you take many bad states and you sort of distill their quality to get a higher quality T state, but you lose some number of them in the process. The way this works is to pick a quantum error correcting code that has a transversal T gate. So a logical T gate on that code can be done by applying a T gate on every single physical qubit. Such codes exist. And then you just basically do error correction on these codes. And so you get a logical T state in those codes that's better than the physical T rotation you can do. But this is a very expensive procedure. So for every T gate that you need to do, you have to do possibly several rounds of this distillation. And so the cost of such a T gate is drastically higher than the cost of a Clifford gate. By how much depends very much on the details, but you should somehow think of these as being much, much more expensive. The next problem then is that when we construct the circuits, we generally liberally use arbitrary rotations. But these arbitrary rotations now in these fault-tolerant platforms, we actually have to translate into a circuit that consists of Clifford gates and T gates. And the goal of this basically is to minimize the number of T gates. But even if you look at more or less optimal algorithms, which were found a couple of years ago, you'll find that a rotation gate by some angle, this is taken from this Klushnikov paper into 2015. So this is by an angle of 0.1, just some arbitrary number, basically. If you want this to an accuracy of 10 to the minus 9 or 10 to the minus 10, the third column here is basically the number of T gates. You need on the order of 100 to 200 T gates to do this single rotation. And then each of those T gates itself needs the whole distillation circuit, and so it's very expensive to come by. And so the high-level picture that I'm trying to get at is rotations are very expensive in a fault-tolerant architecture. So we often draw circuits like this. This is like the local evolution circuit to apply some Hamiltonian term, and we have some Clifford gates like the Hadamard gate and the Y gate and so on, and then we have this arbitrary rotation gate, and this sort of circuit picture suggests that they all cost the same. But really, we should, if we think about time, stretch those rotation gates out by a factor of at least 100, if not more, compared to the Clifford gates. So really, we should draw the circuit like it is on the right, where I've stretched the rotation gates by some large factor compared to, say, the Hadamard gates, because really one rotation is hundreds of times more costly than a Hadamard gate. So that's something important, I think, that we need to keep in mind when we design circuits for fault-tolerant architectures. Let me just very quickly review sort of the experimental status of this field. That's a large and active field, so it's way beyond this talk to do a complete review. But I wanted to point out some highlights, some exciting developments in the last couple of years. So one of the things that was achieved is the extension of the lifetime of a qubit in a post-selected scheme. And so there are actually these at least these two papers, there's probably more, that demonstrate some improvement of sort of a relevant metric of your logical qubit if you do rounds of error correction. Here, it's not really error correction, it's error detection, as in you throw away all the ones where you detected an error, you don't actually actively correct it. That's sort of the next step that I think hasn't quite been taken yet. People have, in various architectures, demonstrated that they can encode a state into a logical qubit with like reasonably high fidelity, and they can check all the stabilizer measurements and see that that they've successfully prepared the qubit, the logical qubit state. And also some of these components of protected operations have been demonstrated. So for example, this surgery operation that's basically doing a logical operation on two surface codes by gluing them together, that's recently been demonstrated in the Innsbruck group. And with that, let me just show these 5 questions that were suggested by the organizers for the breakout discussion sessions. So what is the perspective on future algorithm development? That's such a broad question that I don't really know what to say about it. One question was, what further gains might we expect to see in the next 10 years in logical gate implementation costs? Are there any particular advantages between quantum error correcting codes for the purpose of chemistry? What further gains might we expect to see in the next 10 years on fault-tolerant methods for chemistry, and what types of molecules and chemical problems do fault-tolerant algorithms perform well at? Let me just give a couple of thoughts on some of these questions. So the question on gains on logical gate implementation costs, this seems to be a field that's on a very rapid development right now, with lots of new ideas by tailoring these approaches around specific area, maybe doing computational optimization of the sequences. There's lots of small factors to be had. And so even without major breakthroughs, I think these small factors can accumulate to quite a speed up. But this seems to be something where, I wouldn't be surprised if in 10 years we look at this very differently, even though I can't point sort of specifically at where these improvements will come from. I think an interesting pair of questions is, are there any particular advantages between codes for the purpose of chemistry? Sort of my first as well, the best code is the one we can actually build, and in the end, the hardware devices will be highly optimized around a particular code, even if just because the application, the sort of classical control around it has to be very application specific. Where by application, I mean like a particular combination of code and physical qubit. But maybe an interesting question to think about is, in a fault-tolerant architecture, the errors aren't completely gone. We're just suppressing them by some amount. And, obviously we want to suppress them just enough. One of the things that this to do is to kind of tailor, which errors we can live with and which errors we can absolutely not live with. And sort of make that actually even different for different qubits. So for example, if you think about quantum phase estimation, you have an ancilla qubit, and probably errors on the ancilla qubit would be really bad. But then you have the qubits that are storing the physical state, and maybe you can live with more of those. So you could use for example, in a surface code implementation, a higher distance code for the ancilla qubit than for the physical qubits. Or in the surface codes, you can make them rectangular, and you can suppress X errors much more than Z errors, or vice versa. So if your algorithm can deal with a particular type of error much more, then fault tolerance could be adapted to that. I think this is something we're seeing in sort of the NISQ, where there's some physical type of error, and we try to design algorithms around that. Here it's a little bit the other way around. We can say we have this algorithm, it can deal with this kind of error, but it can't deal with that one. Can we tailor the fault tolerance to sort of have those error characteristics? Then the sort of flip side of this, are there any particular advantages between quantum algorithms for quantum error correcting codes? The thing I already mentioned is that we really need to think about suppressing the number of T-gates. One thing is that non-locality is much less of a problem, I think, in these fault-tolerant approaches because of quantum state teleportation. So you can usually overcome locality with very low, non-locality with very low costs. Maybe one interesting question is, can we at least partially work with the native operations of a code? So for example, in surgery, where the 2-qubit measurements are sort of the elementary operations, so to speak, the assembler instructions of your platform, can we actually design algorithms around that? And then for these last 2 points, what further gains might we expect to see in the next 10 years on fault-tolerant methods? We kind of held a workshop on this, funded by NSF about a year ago, and together with Garnet Chen, Sergey Bravi, and Mario Mada, we wrote a review, taking the input from all the participants of that workshop. I put a link here on the slides. And in that report, we kind of had a list of bullet points of where we see, after the discussions of the workshop, areas for improvement. So I just copied that on here. And I'm not going to go through this, but maybe this is sort of in the discussion session, if particular bullet points here jump out at people, we can follow up on that. So there's 2 slides like this. There's another slide on what types of molecules and chemical problems and also condensed matter problems do these algorithms perform well at. So I just kind of put these bullet points up here, and maybe if people find that, find something that jumps out at them, we can follow up on that. Yeah, I guess now we can go into breakout sessions.